Okay, hi Year 12. Today's video is 3G and it's relating to the applications of maximization and minimization. So what this topic is looking at is actually some real world problems that calculus can assist in solving. We don't often get to look at this sort of stuff in high school. Often that's more of our university level thing. These are good problems and they're ones you'd probably always get in your HSC. So the first one we're going to have a look at is looking at volume and the height of a pool and maximizing that volume. The textbook's got some great examples in there as well. So if you're having a look through the textbook, and I'll pop some of them in the OneNote, some of the practical applications could be things like maximizing the volume of a box built from a rectangular sheet of cardboard, minimizing the fuel used in a flight, and that will have various variables to have a look at. Maximize the profits from manufacturing and selling an article, or minimizing the amount of metal used in a soft drink can. So let's have a look at the first example in your notes. Jump back into those. Okay, so we're just going to basically be using the information that we've learnt so far in the topic in order to answer this question. So the formula for the volume of a pond is given by V is equal to 2h cubed minus 15h squared plus 24h plus 35, where h is the depth of the pond in meters. We want to find the maximum volume of the pond. Okay, so the volume of the pond is going to depend on the height or the depth of the pond in meters. So the maths behind this is no different to what we've been looking at. Your volume basically is your y variable and your h is your x variable. So we're going to be doing exactly the same as before. What you need to look for in these kind of questions is the language that's used in here. So the word here is maximum. So we want to find a stationary point that is a maximum and find out the volume that is relating to that maximum value. And you'll generally always have an equation that is given to you and that we can deal with. So let's have a look at our first bit of information. So we've got V. So we can find V dash. So let's do that to start with. That's going to be 6h squared minus 30h plus 24. And we can also find V double dash, which is 12h minus 30. Okay, so both of those is still a relationship between the volume and the height, which is the depth of the pond in meters. Now, just like we were doing before, we want to find the maximum volume, but in order to do that, we need to find the stationary points. Okay. So stationary points happen when our first derivative, V dash, is equal to 0. So let's set V dash equal to 0. So we're going to have 6h squared minus 30h plus 24. Let's fix up that 30 there. Okay, and we want that equal to 0. So that's a non-monic. But what I would like you to always do when you're getting a non-monic is, first of all, decide if, or have a look at the function to see, can we pull out a common factor to get rid of that 6 at the front? And in this case, we can. If I pop a 6 out the front, I'm going to have a h squared minus 5h plus 4 equals 0. It's a lot easier to factorise. The 6 can stay out the front. So we're looking for values that can multiply to 4 and add to minus 5. We're going to have minus 4 and minus 1. Minus 4 times minus 1 is 4. Yep, that works. Minus 4 plus minus 1 is minus 5. Okay, so we're going to have stationary points of h is equal to 4 and h is equal to 1. Well, they're our first variable. Okay, so our variables are going to take the form of h and v. So I need to find the volume that goes with that height, okay, or that depth of the pond. And these are in meters. Okay, so we're going to have a h of 4 meters. I might just pop that in there. A pond depth of 4 meters and a pond depth of 1 meter. So let's see what our matching volumes for that would be. So when h is 4, we're going to get, oops, sorry, I'm having a bit of a stylus problem there. There we are. Volume is going to be what? And when h is 1, I might fix that up a little bit as well. When h is 1 meter, What's the volume going to be? And our volume is going to be in meters cubed. Okay, so our volume now will be cubic meters, and our volume now will be cubic meters. So that's what volume is. So let's work out our volume. We're going to pop our 4 and our 1 into our function up there. So just pause the video if you need to check the values that I've got. So when I pop 4 into my function up here, I end up with the volume of 147 cubic meters. When I pop 1 in, I get 46 cubic meters. So let's confirm our stationary points. They're 4 and 1, 47, and 1 and 46. Now let's just confirm that we know what the nature of those points are. So the nature of the stationary points. Okay, so to do that, we want to work out our what V double dash is at those. So at 4, 147, V double dash, which is up here, is going to be 12 times 4 minus 30, which is equal to 18. That is positive or greater than 0. So it will be taking that shape, and we will have a minimum at the point 146. V double dash will be equal to 12 times 1 minus by 30, which gives us 12. Take away 30, which is minus 18, which is less than 0, so it is negative, and it is going to be a maximum. So let's have a look at what we're actually looking to find. It says the formula for the volume of a pond is given by this, where H is the depth. Find the maximum volume of the pond. So if you have a look at what we've done down here, I think what most people would have done here, if they weren't sure about their calculus, they would have gone, okay, well, here's a volume on our stationary point that gets us 147 cubic meters. That must be the maximum volume of our pond, but that's not going to be the case. Once we popped our stationary values into the second derivative to find the nature of those, we've discovered that our second derivative gives us a maximum at the point 146. So our maximum volume of the pond will be 46 cubic meters. And we'll pop that down there. The maximum volume of the pond equals 46 cubic meters. Okay, we're going to move down to the second question now. Okay. Rightio. The council wanted to make a rectangular swimming area at the beach using a straight cliff on one side and a length of 225 metres of netting for the other 3 sides. What are the dimensions of the rectangle that encloses the greatest area? If you want to draw a picture, you can, if that helps you. I'm not great at pictures, but I always like to draw the pictures. There's the cliff edge. It wants to make a rectangular swimming area. There are 3 sides here. Might just call them X, Y, and Z. And we know that X plus Y plus Z is going to give us 225 meters. And what the idea is, we're wanting to find the dimensions of that rectangle that encloses the greatest area. So what values of X and Y and Z can we have so that our rectangle's area is the maximum? So I'm going to fix that up a little bit, because what we know is if there's just X and Y, and it's a rectangle, then we've got 2 X's there and a Y, or you might have 2 Y's and an X. And we're going to find that if we add those together, we're going to have 2 X's and a Y, and you get 225. So without even going into too much detail, that's what I've thought about. So let's see what we can do with this question. Okay, so we're going to need to figure out what we know and what we can do with that. So we want to find the dimensions that give us the greatest area. So we need an area. Now let's have a think about it. So if we're going to work out the area of that rectangle, we're going to have the area is the length times the width. Okay, so we need an area. We don't know anything about the area, but we do have a perimeter. We do know that our perimeter is going to give us an X plus, or a 2X, as we had 2 X's there. 2 X's and a Y is going to give us our perimeter. And we also know that we could then write our area as x times y is our area. But we also know, going back down here, that our perimeter is 225, and that equals 2x plus y. So let's see if we can write that in terms of y. So 225 minus 2x is equal to y. That is a formula for our perimeter. That's an equation. I don't know where we're going yet, but let's see if we can call that number 1. Now I'm going to fix my area up here. So I've got my area is x times y, or xy. I've got a formula for y there. My y is 225 minus 2x, and I'm going to times that by my x. It's going to move my equals sign over a little bit. So my x is here, my y comes from here, and if I was to open that equation up, I'd have 225x minus 2x squared. Well, that's my factorized form. But I have a quadratic that I can work with now, okay? So I can find a lot of information there, and it's all going to be dependent on my x here. So I've got 2 variables, I can work with it. So I have an a dash, and I can work out an a double dash. So my a dash, using this equation here, would be 225 minus 4x, and my a double dash would be minus 4. Okay, that's what I know. Let's see where we can go with from there. So let's read the question again. So the council wanted to make a rectangular swimming area at the beach using the cliff on one side and a length of 225 metres, and then find the dimensions of the greatest area. Okay, so we need to find some stationary points before we can do anything else. Stationary points occur at a dash is equal to 0. So we're down here. So 225 minus 4x is equal to 0. So 225 is equal to 4x. What's 225 divided by 4? Pop that in your calculator, and we're going to end up with, I'm just going to leave it as 225 divided by 4, like that. It also equals 56.25. Okay. Okay, rightio, that's our x. Let's find our y. So, when x is 56.25, what's y going to be? We're back into our equation. Well, when I'm looking at y, my y is actually my a, isn't it? So I'm going to pop that as an a. What's my a going to be? My a is going to be 225 times 56.25 minus 2 times 56.25 squared. Pop that in your calculator, and what you'll get is a value of 6,328.125. We are working in meters, and we are looking at square. So we have a stationary point at 56.25, 6,328.125. Okay, so let's just decide if that is going to give us the greatest area. So the greatest area would mean that we would want to have the maximum stationary point happening at that point. So let's see what the nature of our stationary point is. So the nature, what we're going to do is figure out what happens to the second derivative at that point. So at 56, oops, I should put at x equals 56.25. What does our area double dash equal to? It's minus 4, which is less than 0, which is negative, which does give us a maximum. So a maximum turning point does happen here, or a maximum stationary point. So we're on the right track. Now, we still haven't answered the question, so let's go and check again what the question wanted us to do. The question wanted us to find what are the dimensions of the rectangle. Okay, well, our dimensions, we need to just go back to think what our original picture said. So our dimensions were made up of, if I go over to my diagram that I had up here, x and y. So we said that there was, the way that I worked it out was that we had 2 x's and a y. Okay, and that was our perimeter. 2 x's and a y. So, where is our original equation? Let's have a look at this original equation here. Okay, so our dimensions are x is equal to 56.25 meters, and y is going to be equal to 225 minus 2x. 225 minus 2 lots of 56.25. So y is going to equal 112.5 meters. And that will give us the dimension. That will give us the maximum area. So that problem is actually really interesting and really great. So you would be looking at things like this, it's basically a mathematical modeling question in the real world, because you're wanting to get the biggest bang for your buck, basically. We want the biggest area for the minimum price, and then we could bring into cost factors into this and have a look at what the cost per meter of that would be, and that would actually be used out in the real world more than you would expect.